Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Welcome. Settle your breathing, let your body become still, and allow your thoughts to drift outward, slowly, effortlessly, as though they are rising into a calm and quiet sky. Above you, the universe stretches in every direction, a soft ocean of darkness scattered with distant points of light, each one a star, each one a fusion-lit island floating in an endless sea of night. For a moment, simply imagine that vastness, not as something cold or overwhelming, but as a gentle landscape, a place where time moves slowly, and light itself drifts with a quiet, deliberate grace. Tonight, your mind will wander among the largest stars the universe has ever allowed to exist, ancient titans of hydrogen and helium, hypergiant stars so immense that even the sun would look small beside them, so wide that their surfaces could stretch far beyond the orbit of Earth, so luminous that their radiance would outshine millions of ordinary stars combined. Yet even with their staggering size, their overwhelming brightness, and their unimaginable power, there is a stillness to them, a tranquil presence that fills the dark with a slow and patient glow. As you breathe gently, picture these colossal stars resting in the quiet of space, their outer layers drifting, their light traveling across unimaginable distances before reaching us. Their existence marked not by haste, but by a calm, steady burn. You do not need to hold on to every detail tonight. There is nothing to memorize, nothing to analyze with effort. You may let the science wash through you, softly, naturally, as though it were a quiet current guiding you toward rest. All you need is the feeling of immensity, the soft sense of drifting near stars so vast they challenge intuition. The awareness that the cosmos contains objects so large they cannot be fully pictured, only felt, like distant lanterns glowing across a silent sea. Hypergiants live brief, extraordinary lives, but from this peaceful distance, their stories unfold slowly, delicately, like waves spreading across a quiet shore. And here, far from noise, far from responsibilities, you can simply float with them, letting their light settle gently over your mind. So rest, breathe, and let the universe open around you, one soft star, one quiet thought, one drifting moment at a time. The journey begins now. Imagine, for a moment, that you could stand far outside our galaxy, far beyond its spiral arms, looking back at it from a quiet vantage point in intergalactic space. From that distant viewpoint, you would see the Milky Way as a soft, glowing disk, a flattened whirlpool of starlight, its billions of stars blending into a hazy, luminous mist. Most of those stars are modest, small, steady suns not so different from our own, quiet, long-lived, and relatively stable. But scattered through that disk, in star-forming regions, in dense clouds of gas and dust, there are a few that do not fit this gentle pattern. They are not merely larger than average, they are giants among giants. Enormous, unstable, brilliant beyond easy description. These are the hypergiant stars. To understand what makes a hypergiant different, it helps to start with something more familiar. Our Sun is a main sequence star, a star in the long, stable middle chapter of its life. It fuses hydrogen into helium in its core, releasing energy that balances the inward pull of gravity. For billions of years, this balance remains calm and steady. Some stars are born with more mass than the Sun, perhaps 10 times or 20 times or 30 times the Sun's mass. These more massive stars shine brighter, live shorter lives, and evolve more dramatically. As they exhaust the hydrogen in their cores, they swell and cool at their surfaces, expanding into red supergiants, or sometimes shifting through blue and yellow supergiant phases. They are large, luminous, and impressive. But hypergiants exist another step beyond even these massive supergiants. The term hypergiant is not defined by a single simple number, There is no exact mass or exact radius or exact luminosity where a star suddenly becomes a hypergiant. Instead, it is a category used for the most extreme, unstable, and luminous stars we know, stars that press close to the limits of what stellar physics can support. In general, a hypergiant is a star with a very high mass, often tens of times the mass of the Sun, and in some cases perhaps close to 100 times the Sun's mass or more. It radiates energy at an astonishing rate, often millions of times the luminosity of the Sun, and it shows clear signs of instability, strong mass loss, and complex, extended atmospheres. If you could place such a star where the Sun is now, its surface might expand far beyond Earth's orbit, and in some cases even beyond the orbit of Jupiter. The star's radius could be hundreds, or even over 1,000 times the radius of the Sun. When we speak of hundreds of solar radii, we are not just enlarging the Sun in our imagination, we are creating a glowing sphere so vast that it would fill a large fraction of the inner solar system. Picture the orbit of Earth around the Sun, a nearly circular path at a comfortable distance. Now imagine a star so large that its outer layers would engulf that orbit completely. Earth would be buried deep inside its atmosphere, bathed in an overwhelming brilliance. Some hypergiants are cooler at the surface, with temperatures not very different from a red supergiant. These stars radiate most of their energy in the red and infrared parts of the spectrum. Others are hotter, blue or white in color, their surfaces heated to tens of thousands of degrees. In both cases, they are extraordinarily luminous. If you were to compare their brightness with that of the Sun, you might find that a single hypergiant from a great distance outshines millions of suns like ours combined. But luminosity is not just a visual spectacle. It is a measure of how much energy the star is producing every second. Energy created in the core by nuclear fusion and transported outward through layers of gas until it escapes into space as light and heat. For a star, gravity pulls inward, while the pressure from hot gas and radiation pushes outward. In a stable star, these forces balance. The outward pressure exactly counters the inward pull of gravity, and the star neither collapses nor explodes. In very luminous stars, radiation plays a more and more important role. Every photon escaping from the hot interior carries momentum. When photons are absorbed or scattered by atoms in the star's outer layers, they push on that gas, imparting a gentle but persistent outward force. As the luminosity increases, this radiation pressure grows stronger. There is a particular luminosity, known in astrophysics as the Eddington limit, at which the outward push from radiation on the gas becomes as strong as gravity's inward pull. When a star's luminosity approaches this limit, its outer layers become only marginally bound to the star. Hypergiants live perilously close to this threshold. Their luminosities are so high, and their outer layers so extended and tenuous, that radiation pressure can easily lift material away from the star, driving powerful stellar winds and making their atmospheres unstable. This is one of the defining traits of hypergiants. They are not simply big and bright, they are also fragile in a sense, balanced on the edge between cohesion and dispersal, where a more ordinary star might have a relatively compact, well-defined surface. A hypergiant often has an atmosphere that is thick, extended, and highly structured. Its photosphere, the region from which most visible light escapes, is not a sharp boundary, but a fuzzy, shifting layer that moves in and out over time. Within those outer layers, convection and turbulent motion move heat outward. Giant convective cells, much larger than our entire solar system, rise and sink slowly in the star's envelope. These motions stir the gas, causing local brightening and dimming, and sometimes launching material outward. If you could watch the surface of a hypergiant up close, it would not look like a smooth, calm disk. Instead, you would see huge patches and plumes, regions where gas is rising hotter and brighter, and others where it is cooler and sinking. The atmosphere would appear to seethe, as if it were boiling on scales far larger than any planet. The gas in those layers is not perfectly transparent. Its opacity, the degree to which it absorbs and scatters light, depends on temperature, density, and chemical composition. In certain ranges of temperature, small changes in conditions can greatly increase the opacity, making it harder for radiation to escape and causing local buildups of energy. These pockets of increased opacity can drive further instabilities. As radiation accumulates behind them, pressure rises, and the gas may expand violently outward only to cool, become more transparent again, and then settle until the cycle repeats. In this way, a hypergiant's outer envelope is in constant motion. It is not a rigid shell, but a restless, turbulent region where radiation, gas pressure, and gravity compete. Because they live so close to the Eddington limit, hypergiants lose mass at extreme rates. They blow powerful stellar winds, streams of gas flowing away from their surfaces at many hundreds of kilometers per second, and sometimes much faster. The Sun also has a stellar wind, a continuous outflow of charged particles that spreads through the solar system. But compared to a hypergiant's wind, the Sun's outflow is gentle, almost delicate. A hypergiant can lose as much mass in a few thousand years as the Sun will lose in many billions of years. The mass loss rate can be millions of times greater, transforming the star's structure over relatively short periods of time. The material blown off by these winds does not vanish. It accumulates around the star, forming extended envelopes of gas and dust. Often we see hypergiants surrounded by glowing nebula, shells or arcs or irregular clouds of material ejected in previous episodes of strong mass loss. Observations in visible and infrared light reveal intricate shapes, clumps, filaments, and arcs, all sculpted by the interactions of winds, radiation, and sometimes the star's motion through the surrounding medium. This intense mass loss is another key feature that distinguishes hypergiants from ordinary supergiants. A star may be large and bright, but without strong, persistent mass loss and clear signs of instability, it is usually not classified as a hypergiant. All of this extreme behavior has another consequence. Hypergiants do not live long. A star's lifetime is primarily determined by its mass. The more massive the star, the more hydrogen it has available to fuse. But mass is not the only factor. Equally important is how quickly the star uses that fuel. Massive stars burn their nuclear fuel at a ferocious rate. Their cores are hotter, fusion reactions proceed faster, and their luminosities are much higher. This means they exhaust their hydrogen and helium far more quickly than a star like the Sun, where the Sun might shine steadily for about 10 billion years. A very massive star may live only a few million years, or even less, before it begins to run out of core fuel and evolve toward its final stages. Hypergiants sit near the extreme end of this trend. They are so luminous, so energetically intense, that their lives are particularly brief, some lasting only a small fraction of the time that even a typical massive star survives. Their short lifespans, combined with the rarity of forming such massive stars in the first place, help explain why hypergiants are so uncommon. Stars form in cold, dense molecular clouds, regions where gravity can pull gas together into clumps. If a clump gathers enough mass, it can collapse and form a star. But to make a hypergiant, a particularly massive clump is required, one that can channel tens of solar masses into a single object. Most of the time, gas in a cloud is divided among many forming stars, dozens, hundreds, or even thousands, sharing the available material. Only rarely does enough mass funnel into one core to create a star that might become a hypergiant. Even when a very massive star does form, it will not remain in the hypergiant phase forever. It may pass through brief episodes of extreme luminosity and instability before evolving into another kind of luminous star or collapsing in a catastrophic explosion. Taken together, these factors mean that, in an entire galaxy of hundreds of billions of stars, only a handful may be true hypergiants at any given time. Imagine walking through a city at night. Most of the windows are lit modestly, soft yellow light spilling out onto the streets. Occasionally, you see a building with brighter lights, perhaps a theater or a large hall. Hypergiants are like the rare buildings whose entire faces blaze with intense light, so bright that they illuminate the street around them. Yet inside, everything is restless, in motion. Straining the structure itself, they are objects at the upper edge of what gravity and radiation can hold together, overgrown stars whose own light is nearly strong enough to unbind them. When astronomers classify stars, they look not only at their brightness and temperature, but also at the features in their spectra, the specific patterns of dark and bright lines formed as light interacts with the atoms in the star's atmosphere. Hypergiants typically show broad, complex spectral lines, evidence of powerful winds and turbulent outer layers, Their spectra may contain signatures of outflowing gas and of dense, extended envelopes that scatter and absorb light. These observational clues, combined with their enormous luminosities, lead astrophysicists to place them in the hypergiant category. So when we say that hypergiants are the largest stars known, we are speaking not only of their volume, but also of their place in the physics of stars. They are the extreme cases where mass, luminosity, and instability come together. They differ from ordinary massive stars in several fundamental ways. They are generally more massive, often tens of times the Sun's mass. They expand to much greater radii, hundreds or more solar radii in size. They shine with far higher luminosity, often millions of times the Sun's output. They live close to the limit where radiation pressure can balance or even overcome gravity, making them unstable and prone to heavy mass loss. Their surfaces are restless, boiling with convection, turbulent and variable. They lose matter through intense winds, at rates millions of times greater than the Sun's, surrounding themselves with shells and clouds of expelled gas and dust. And because of their enormous energy output, they burn through their nuclear fuel rapidly, leading to short, spectacular lives and rare appearances in the galaxy. Hypergiants are, in a sense, the universe testing how large and luminous a star can be, before it begins to fall apart under its own brilliance. As you rest, you can imagine these stars as vast, glowing spheres suspended in the dark, their outer layers drifting and shifting, their winds carrying material out into space, their light flowing steadily across the void. They are not calm in their interiors, but from where you drift, far away and unhurried, they seem like silent beacons, marking the upper boundary of what a star can become. And somewhere in the Milky Way, and in many other galaxies beyond, a few of these titanic stars are shining right now, their light already on its way to us, crossing millions of years of empty space to arrive as faint points in the night sky. You may never know which distant dot is a hypergiant, or which faint star once passed through that brief and dramatic stage, but tonight, as you breathe slowly, you carry the knowledge that such objects exist, quietly, majestically, holding themselves together on the thin edge between gravity and light. Far out in the darkness, among the spiral arms and star-forming clouds, you can imagine a quiet census of stars taking place. Most stars would fall into familiar groups: small red dwarfs, medium yellow suns, blue-white giants. But if you look only for the most extreme cases, for the ones whose luminosity pushes the limits of what gravity can contain, you are searching for hypergiants. They are not defined by a single sharp line, not by one exact mass or one precise radius. Instead, they occupy a region near the top corner of the diagram astronomers use to classify stars, the region where luminosity is very high, and the stars are swollen to extraordinary sizes, and their atmospheres are clearly unstable. If you could weigh these stars, you would find that many of them began life with perhaps 30, 50, or even close to 100 times the mass of the Sun. Some candidates might be even more massive, though the exact numbers are difficult to pin down, because their powerful winds strip away mass over time. This is one reason there is no strict boundary. A star that begins with perhaps 70 times the Sun's mass could lose a large fraction of that material as it evolves, yet still shine with hypergiant luminosity. For that reason, astronomers tend to focus less on initial mass and more on what can be observed directly now: luminosity, spectral features, and signs of intense mass loss. The radius of a hypergiant is also not fixed. It depends on the star's temperature, its internal structure, and its stage of evolution. A hot blue hypergiant may not seem as physically large as a cool red one, yet its luminosity can still be extreme, because higher surface temperature means each square meter radiates more energy. On the other hand, a cool red hypergiant may expand to a truly enormous radius, hundreds or over 1,000 times the Sun's radius, its surface temperature lower, but its surface area so vast that the total light it radiates remains immense. If the Sun were shrunk to the size of a small coin in your hand, a hypergiant might be a glowing sphere the size of a large house, or even an entire city. The comparison is not exact, but it hints at the scale difference, one star swollen far beyond the proportions we are used to imagining. The luminosity, the total power output, is the key. A typical hypergiant shines with the energy of hundreds of thousands or millions of suns, Energy production in the core scales very steeply with mass. When you add more mass to a star, its core becomes hotter and denser, fusion reactions proceed more rapidly, and the star's brightness climbs dramatically. But that increased luminosity comes with a cost. The outward push from radiation grows stronger, and the star moves closer to the regime where light itself is almost strong enough to blow the star apart. The idea of the Eddington limit captures this balance. In essence, it is the luminosity at which radiation pressure on the star's atmosphere equals the inward pull of gravity. If a star's luminosity exceeds that limit by too much, its outer layers can no longer remain in place and must be driven off into space. Many hypergiants sit uncomfortably near this boundary. Their luminosities are so high that small changes in internal structure or in the opacity of their gas can push portions of their atmosphere over the edge. Those outer layers then respond dramatically. They may puff outward, becoming more extended and diffuse, or they may be expelled in sudden outbursts, creating shells and arcs of gas around the star. Because of this, hypergiants cannot be thought of as calm, static spheres. They exist in a state of perpetual negotiation between gravity and light, between cohesion and loss, between being a single star and becoming a cloud of debris. This persistent imbalance shows up in their stellar winds. Every star emits some form of wind, a continuous flow of particles escaping its gravity. For the Sun, this wind carries a small amount of mass away over long timescales, barely altering the Sun's overall structure. For a hypergiant, the situation is very different. Its winds can remove mass at rates millions of times higher than the Sun's wind. In a single year, a hypergiant can lose as much matter as the Sun might shed in tens of thousands or hundreds of thousands of years. Over the relatively brief lifetime of such a star, these winds can peel away much of its outer envelope, altering its composition, its radius, and even its future evolution. This fierce mass loss is not uniform. It can vary with time and can be channeled into complex structures by magnetic fields, rotation, and interactions with surrounding gas. When astronomers observe hypergiants, they often detect extended nebulae around them, built from material cast off in previous episodes of strong wind or eruption. These nebulae can stretch for many times the radius of the star itself, glowing softly as they reflect and absorb the star's light. They are, in a sense, fossil records of the star's instability, each shell a memory of a time when the balance between radiation and gravity briefly failed, and the star breathed out a deep, massive exhalation of gas. The surfaces of hypergiants are equally restless. In a less massive star, the surface layers might be relatively well behaved, marked by granules of convection and occasional flares, but overall stable. In a hypergiant, convection becomes a dramatic, large-scale phenomenon. Giant convective cells, each spanning a significant fraction of the stellar radius, carry energy outward, rising and falling over long timescales. These cells can create bright regions and dark patches, local hot zones and cooler areas, giving the photosphere a mottled, uneven appearance. Because the gas is partially opaque, changes in temperature and density can cause changes in opacity, making it easier or harder for light to escape from different regions. Where opacity increases, radiation can be trapped temporarily, leading to localized buildups of pressure, which then drive expansion, cooling, and eventual release of energy. Where opacity decreases, light flows more freely and gas can contract. This constant adjustment creates a complex and dynamic surface, with waves, pulsations, and irregular brightness variations. From our vantage point on Earth, these processes appear as slight changes in the star's brightness over time, or as subtle shifts in the shapes of spectral lines, signatures of moving, accelerating, and expanding gas. When astronomers examine these spectra, they often see evidence of gas flowing outward at high speeds, lines broadened and shifted by the Doppler effect, indicating velocities of hundreds of kilometers per second or more. The presence of strong winds, extended envelopes, and irregular variability, combined with extreme luminosity, are the practical markers used to identify a star as a hypergiant. All of this activity plays out over a surprisingly short interval of cosmic time. Stars like the Sun can live for billions of years, spending the vast majority of that time in a relatively quiet, stable phase of core hydrogen fusion. Hypergiants, by contrast, burn through their fuel at an astonishing rate. Their core temperatures and densities are so high, and their energy output so intense, that their store of hydrogen is consumed rapidly. Instead of billions of years, their main sequence phase may last only a few million years, and the later hypergiant phases may last just a fraction of that, brief flashing episodes on a galactic timescale. From the perspective of the Milky Way, a hypergiant's entire life is almost like a spark, bright, transformative, and quickly gone. This brevity, combined with the difficulty of forming very massive stars in the first place, makes hypergiants rare. To create such a star, a molecular cloud must not only be massive enough, but must also deliver a large amount of that mass into a single collapsing core. That requires particular conditions, and even when they are present, feedback from radiation and winds can limit how much gas ultimately accretes onto the forming star. Only a small fraction of star-forming regions will ever produce a hypergiant candidate, and once such a star forms, it spends only a short time in recognizable hypergiant phases, before evolving further, or ending its life in a supernova or direct collapse. The result is a combination of rarity in formation and brevity in lifetime, in the entire disk of the Milky Way. With its hundreds of billions of stars, only a handful at any given moment are in this extreme category. If you imagine the galaxy as a vast forest of stars, hypergiants are like a few towering ancient trees, colossal in height and breadth, but fragile and destined to fall sooner than the smaller, tougher trunks around them. From far away, their crowns rise above the canopy, catching more sunlight, but also more wind and more strain. The hypergiant's luminosity is their glory, and also their undoing. This, in essence, is what distinguishes hypergiants from ordinary massive stars, and even from typical supergiants. They are more massive at birth, they reach larger radii, they shine more intensely, their atmospheres are more extended and unstable, their mass loss rates are far higher, their lifetimes are much shorter, and they occupy a thin, precarious zone near the maximum luminosity a star can sustain without tearing itself apart. When you look up at the night sky, you do not see these details. You see only points of light, some bright, some faint. Yet hidden among them, in the crowded regions of the Milky Way, a few rare stars are living out these hypergiant lives, glowing with a brilliance that defies simple comparison, their outer layers drifting away into the dark, their cores racing through the stages of nuclear burning. As you rest, you can let this knowledge settle softly in your mind. The universe does not fill itself only with ordinary objects. It also explores extremes, testing the boundaries of what matter and energy can do under gravity's rule. Hypergiant stars are one of those experiments, brief, difficult to sustain, but spectacular. They are the most luminous, most swollen, and most unstable forms that a star can take, without instantly unbinding itself. They live on the edge, held together by a delicate balance between gravity and the pressure of light, losing mass in great streams and shells, shining with the energy of millions of suns, yet doomed to burn out quickly. Knowing this, you can picture them in the dark of space, not as violent monsters, but as immense, delicate structures, glowing quietly, slowly changing, slowly losing themselves to the winds they create. And somewhere between those distant colossi and the small, steady star that warms Earth, you are resting now in a quiet room on a small planet, with a mind capable of holding both scales at once. You can feel the smallness and the vastness together. And you can let that perspective loosen the tightness of the day as you drift gently into the deeper stories these enormous stars will tell. Imagine drifting slowly into the heart of a vast, cold cloud of gas and dust. From a distance, this cloud looks like a dark patch against the brighter background of the Milky Way, a silhouette where starlight is swallowed rather than scattered. Inside, however, there is structure, filaments, knots, and regions where gravity has begun to gather matter together. These are molecular clouds, the birthplaces of stars. They span many light years and contain enough gas to build thousands or even millions of suns. Within such a cloud, small disturbances can grow. A passing shock wave from a supernova, the tidal pull of nearby structures, or the slow internal motions of the gas itself, can cause parts of the cloud to become slightly denser than their surroundings. Where the density is higher, gravity pulls a little more strongly, gas flows inward, increasing the density further, and a runaway process begins. Many stars form from relatively modest clumps within these clouds. Each clump collapses, fragments, and shares its material among a cluster of forming stars. Most of those future stars are small, somewhat like the Sun, or even less massive. To make a future hypergiant, the initial conditions must be different. Instead of fragmenting into many equal parts, a large fraction of the local gas must funnel into a single collapsing core. The clump must be massive, tens of times the Sun's mass or more, and it must deliver that mass quickly enough that radiation from the forming star does not blow the gas away too soon. As the clump collapses, its central region grows denser and hotter. Eventually, a protostar forms in the middle. Surrounded by an envelope of infalling gas and often a rotating disk. Even before true nuclear fusion begins, gravitational energy is converted to heat. The core warms and the forming star begins to shine weakly, not from fusion yet, but from the energy of contraction. In a modest protostar, this contraction can proceed gradually. The object takes its time, approaching the conditions needed to ignite hydrogen in a relatively gentle way. In the case of a massive protostar on its way to becoming a hypergiant, everything is more intense. The higher mass means stronger gravity, which compresses the core to higher densities and temperatures more rapidly. Radiation pressure starts to build, and the forming star shines brightly already during its infancy. This radiation pushes back on the surrounding gas, trying to halt the infall. For a very massive forming star to continue growing, it must somehow keep pulling gas in, even while it shines strongly enough to repel it. Accretion flows can become focused, perhaps along certain directions where the radiation is less effective at driving material away. Magnetic fields and rotation can help channel gas down toward the forming star, through disks and funnels. The details are complex and an area of active research, but the broad picture is clear. Only in a small subset of circumstances can a single protostar amass enough material to later evolve into a hypergiant. Once enough mass has been gathered at the center, the temperature and pressure in the core become sufficient to ignite hydrogen fusion. This is the critical moment when the object truly becomes a star. For a hypergiant progenitor, core fusion begins at temperatures far higher than those inside the Sun. The dominant fusion pathway is not the simple proton-proton chain that powers stars like our own. Instead, the carbon-nitrogen-oxygen cycle, which is more efficient at higher temperatures, takes over. Hydrogen nuclei fuse into helium using carbon, nitrogen, and oxygen as catalysts, and the energy output soars. The newborn star quickly finds its place on the main sequence band of the temperature-luminosity diagram, but its position is far above and to the left of the Sun, hotter, brighter, and more massive. In this initial phase, the star is not yet a hypergiant. It is a very massive, very luminous main sequence star, burning hydrogen in its core at a ferocious rate. Over time, the core hydrogen supply dwindles. The star has so much mass, and its central temperatures are so high, that hydrogen is consumed in only a few million years, a tiny fraction of the Sun's expected lifetime. When the core hydrogen is exhausted, the star can no longer sustain the same pressure through that form of fusion. The balance between gravity and internal pressure is disturbed. The core begins to contract under its own weight, heating further as it does. Around the shrinking core, a shell of hydrogen still remains. Under the influence of the contracting core's gravity, this shell heats up, and hydrogen fusion ignites there instead, in a ring surrounding the core rather than at its center. The added energy from this shell burning pushes the outer layers of the star outward. The star's envelope expands and its surface cools. This is the beginning of its journey into the giant and supergiant phases, as it swells in size and shifts in color. For a very massive star, the expansion can be dramatic. The radius may increase by hundreds of times, and the star may move across the temperature-luminosity diagram from the blue, hot side toward the cooler, red side. At certain points in this evolution, as the star becomes extraordinarily luminous and extended, and as its atmosphere becomes unstable and loses mass at high rates, astronomers classify it as a hypergiant. Inside the star, the story continues to grow more layered. As the core contracts and heats after hydrogen is gone, it eventually reaches the conditions needed to ignite helium fusion. Helium nuclei combine to form carbon and oxygen, releasing energy and halting the core's collapse for a time. Around that helium-burning core, shells of hydrogen and helium burning can coexist. Hydrogen may be fusing into helium in an outer shell, while helium fuses into heavier elements in an inner region. Later still, as helium is exhausted in the core, the process repeats. The core contracts again, heating until carbon burning can begin, forming neon, sodium, and magnesium. Then neon burning, oxygen burning, and silicon burning follow, each stage producing progressively heavier elements, and each proceeding more rapidly than the last. This creates a structure somewhat like an onion, with multiple shells of fusion: hydrogen, helium, carbon, neon, oxygen, and silicon burning at different depths, all surrounding an increasingly dense inner core. From the outside, you see only a single star, glowing with brilliant light. But inside, it is a stacked system of active fusion regions, a nested series of burning shells. Throughout this time, the star's outer layers respond to changes in energy generation and internal structure. When energy production increases temporarily, the outer layers can expand and cool. When it decreases, the layers can contract and heat. These changes are not smooth. They can be accompanied by pulsations, oscillations in which the star's radius and brightness vary with time. Some of these pulsations resemble those seen in Cepheid variables, where the outer layers alternately compress and expand, changing the star's brightness in a somewhat regular cycle. In a hypergiant, pulsations can be more irregular and complex, dominated by the interplay of convection, radiation pressure, and changing opacity in the envelope. As the star expands, its surface area grows, but its surface temperature may drop. If the effective temperature decreases, the star radiates more of its energy in red and infrared light. Even so, its total luminosity can remain extremely high, because the increased area more than compensates for the lower temperature. As the star contracts again, the surface temperature increases, and the peak of its emission shifts back toward shorter wavelengths. Its color becomes bluer, and its brightness in visible light can change. Over long periods, these expansions and contractions can move the star between different spectral classes. A massive star may begin as a hot blue supergiant, evolve into a yellow hypergiant phase, then swell further into a red hypergiant stage, and sometimes contract back toward the blue again as mass loss and core evolution continue. During each transition, the coupling between internal energy generation and the outer atmosphere is imperfect. The star overshoots and readjusts, like a system trying to find equilibrium but never quite succeeding. This is why hypergiants can show large, slow variations in brightness, and occasionally sudden outbursts when material is expelled. Atmospheric shocks can form as pulsations and convection drive waves outward. These shocks can heat gas locally or accelerate it outward into the wind. They may compress regions of the envelope, affecting where and how dust forms. In some cases, dense clumps in the envelope can cool enough for tiny solid grains to condense, forming dust that absorbs and re-radiates the star's light in the infrared. This dust can be carried outward by the wind, contributing to the extended nebulae observed around many hypergiants. Step by step, mass loss modifies the star's outer layers. As the hypergiant sheds its envelope, the ratio of core mass to total mass increases. This can make the star more compact in later stages, and can influence which evolutionary path it follows. A star that has lost a great deal of mass might eventually appear as a hotter, more compact object, its outer hydrogen-rich layers peeled away, revealing more processed material beneath. In this sense, mass loss is not just a side effect of hypergiant behavior. It actively shapes the star's future, deciding whether it becomes a certain type of supernova or a different kind of luminous object before its final collapse. Throughout all of this evolution, one trait remains constant. The star never fully settles. At every stage, its high luminosity keeps it close to the threshold of stability. Radiation pressure continually challenges gravity's hold on the outer layers. Changes in core burning stages send waves of adjustment outward, and the envelope responds with expansion, contraction, pulsation, and wind. If you imagine the star as a living being, it is always breathing heavily, never quite at rest, drawing in, pushing out, circulating energy from its center to its surface in great, slow, convective motions. As it approaches its final phases, the pace of internal change accelerates. Later fusion stages, such as carbon, neon, oxygen, and silicon burning, proceed much more rapidly than hydrogen and helium burning did. Hydrogen burning in the core might have lasted for millions of years, helium burning perhaps for hundreds of thousands of years, carbon burning for only thousands of years, and silicon burning for days, or even less. During these final stages, the star's core is assembling an iron-rich center, an inner region where fusion can no longer release net energy. Iron and nearby elements in the periodic table are the point where further fusion consumes energy rather than providing it. While this iron core grows, the outer shells continue to burn, and the hypergiant continues to shine brilliantly. But the end is being prepared quietly, deep inside, as the core edges toward a mass and density that can no longer support itself against gravity. From the outside, the star may still appear as an enormous, luminous object, with strong winds and an extended envelope. Its light still pours out across space, and yet its remaining lifetime is now very short compared to the ages of galaxies and planets. It is on the slow but certain path toward collapse, toward the moment when the iron core will give way, and the star will experience its final transformation. For now, you can picture this entire arc of evolution as a single continuous breath in cosmic time, from the cold birth in a molecular cloud, to the rapid ignition of a massive core, to the swelling into hypergiant phases with multiple fusion shells and unstable envelopes, to the gradual buildup of heavier and heavier elements at the center. At every step, the star balances on the edge between gravity and light, between cohesion and dispersal, between being a single object and becoming part of the interstellar medium once more. And while this complex story unfolds over millions of years, you can let it pass through your thoughts in a matter of minutes. Your breathing stays slow and steady, your body remains still, and your mind drifts through these immense, patient changes, watching a star's lifetime stretch and compress, until it becomes the quiet rhythm of inhalation and exhalation. Somewhere, in the dark beyond our own sun, hypergiant stars are in these very stages right now, just as others have already completed them, and others have yet to begin. They rise from clouds, ignite, expand, shed their layers, and move steadily, inevitably, toward their final collapse. And as you rest, you float alongside them, unhurried, simply witnessing the way matter and energy, under gravity's guidance, can become something so vast and so transient at the same time. Out in the constellation of the Great Dog, in a region of the sky that to the naked eye seems calm and ordinary, there exists a star so large, so swollen and extended, that it has become one of the icons of hypergiant astronomy, VY Canis Majoris. From Earth, even with a telescope, it looks like a faint point of reddish light, not especially impressive to the unaided eye, because it lies far away, buried in the clutter of the Milky Way's disk. But when astronomers measure its brightness, its spectrum, and the way its light interacts with the surrounding gas and dust, they infer a star of extraordinary size. VY Canis Majoris is a red hypergiant, with a radius that has been estimated to be hundreds, or perhaps more than 1,000 times the radius of the Sun. The exact value is uncertain, because its atmosphere is extended, patchy, and partly hidden by dust. But whether the true number is closer to 500 or to over 1,000 solar radii, the message is the same. This is a star that, if placed at the center of our solar system, would stretch beyond the orbit of Mars, and perhaps approach or exceed the orbit of Jupiter. Its swollen envelope would engulf the region where the inner planets now circle, turning those familiar orbits into paths through its own atmosphere. Around VY Canis Majoris, astronomers have mapped an intricate nebula of expelled material. Multiple arcs and clumps of gas and dust surround the star, relics of past episodes of strong mass loss. These structures, seen in visible and infrared images, form a kind of chaotic halo, asymmetrical, fragmented, evidence that the star does not shed its mass quietly and evenly, but in powerful, localized outflows and eruptions. Each arc carries away part of the star's outer layers. Each clump marks a moment when the balance between radiation pressure and gravity tipped, and a portion of the envelope was driven into space. When you picture this star, you can imagine a vast, ruddy sphere, surrounded by drifting clouds, illuminated by its own light, the whole scene set against the smooth darkness of the interstellar medium. Many light years away from VY Canis Majoris, in the direction of the small constellation of the Shield, lies another hypergiant that has captured astronomers' attention. Scuti. This star has often been described as the largest known star by radius, at least among those measured so far. Its estimated radius is again in the realm of hundreds to more than 1,000 solar radii. The exact value is debated and may be revised as measurements improve, but whatever the precise number, its scale is staggering. To give a sense of its volume, imagine how many suns would fit inside it, not side by side on a flat surface, but filling a three-dimensional sphere. The answer reaches into the billions. Consider also the solar system. If Scuti were placed where the Sun is now, its surface would extend well beyond the orbit of Mars and likely beyond the orbit of Jupiter, perhaps even close to the path of Saturn, depending on the exact radius used. The empty space that now separates the inner planets from the gas giants would be filled with stellar matter, tenuous, hot, glowing, a vast atmosphere of hydrogen and heavier elements. Seen from a distant vantage point, this gigantic star would loom across the sky as a colossal disk of light, occupying an area far larger than the Sun or Moon do in Earth's sky. Its presence would be overwhelming. Yet from where we actually stand, on a quiet planet many thousands of light-years away, it is just one more faint point, barely perceptible without instruments. The contrast between that immense reality and the smallness of its appearance as a dot of light is part of what makes hypergiants so quietly astonishing. In another galaxy, the Large Magellanic Cloud, which orbits the Milky Way like a small companion, astronomers have found a red hypergiant with a somewhat unusual environment. W8G64. This star is surrounded not just by a diffuse cloud, but by a thick, rather torus-shaped distribution of dust, a kind of dense ring or donut of material that encircles the star at a distance. The dust absorbs much of the star's visible light, re-radiating that energy in the infrared. As a result, W8G64 appears especially bright in infrared observations, standing out in wavelengths where cooler dust and gas shine. This dusty torus suggests that the star has undergone strong, perhaps directional mass loss. The outflow of gas may have been shaped by rotation, magnetic fields, or interactions with surrounding material, funneling matter into certain preferred directions rather than expelling it evenly. From a sleep-soft vantage point, you can imagine this star as a red, slowly pulsing heart wrapped in a dark, thick ring of dust, its light leaking out through gaps and glowing faintly in the surrounding gas. Closer to home in our galaxy, there are other hypergiant examples with their own peculiarities. RW Cephei is a red or orange hypergiant in the constellation Cepheus. It is highly luminous and very extended, with a mass loss rate that has created an envelope of material around it. Its brightness varies irregularly, and its spectrum shows complex features from its extended atmosphere and wind. It stands as another reminder that hypergiants are not a single, standard type, but a diverse group of stars that share extreme luminosity and instability. HR 5171A is a yellow hypergiant system that is particularly intriguing. It is actually part of a close binary pair, where two stars orbit each other so tightly that they share a common envelope, touching or nearly touching, like two droplets of liquid that have flowed together but not fully merged. This contact binary configuration means that mass can be exchanged between the stars, and their mutual gravity shapes their outer layers in complex ways. The result is a distorted, pear-shaped or elongated stellar envelope, rather than a perfect sphere. From afar, this system appears as a single luminous object, but detailed observations reveal its binary nature. Its structure and evolution are heavily influenced by the gravitational dance of its two components. Again, the theme emerges. Hypergiants often live complicated lives, shaped not only by their own internal physics, but by their environment, their winds, and in some cases, their companions. There are also stars that are not quite hypergiants, but sit nearby in the hierarchy of luminosity and size, luminous blue supergiants that act as points of comparison. In the familiar constellation of Orion, Epsilon Orionis and Rigel are prime examples. Rigel, the bright blue-white star that marks one of Orion's feet, is a luminous blue supergiant. It is much more massive and luminous than the Sun, and it plays a significant role in illuminating the surrounding gas and dust in its region of space. Epsilon Orionis, near the belt of Orion, is also a bright, massive star, with high luminosity and strong winds. These stars are not classified as hypergiants. Their spectra and mass loss rates place them below that most extreme category, but they still demonstrate the broader family of massive luminous stars that hypergiants belong to. Comparing them helps astrophysicists understand what makes hypergiants special. The difference is not simply size or brightness, but the combination of extraordinary luminosity, proximity to the radiation pressure limit, and clear signs of heavy mass loss and instability. When you stand back and consider all these stars together, VY Canis Majoris, UI Scuti, WOHG 64, RW Sif HR 5171A, and luminous blue supergiants like Rigel, you see a mosaic of extreme objects, each with its own story, yet all showing how varied the upper end of stellar evolution can be. Measuring these stars is not straightforward. For smaller and more compact stars, we can often treat their surfaces as relatively sharp boundaries. The radius can be defined in a simple way, based on where the optical depth, a measure of transparency, reaches a certain value. For hypergiants, the situation is messier. Their atmospheres are extended and diffuse. There is not a clear, hard edge, but a gradual thinning of gas into space. Their photospheres may shift in and out with time, as the star pulsates or as convection changes local conditions. Dust around the star complicates matters further. It absorbs and scatters light, making the star appear dimmer or redder in some directions and brighter in certain wavelengths than in others. As a result, when we quote a radius for a hypergiant, we are really giving an approximation, a characteristic scale that depends on modeling, on assumptions about temperature, brightness, and how the atmosphere is structured. Different methods can yield different values. Interferometry, which uses multiple telescopes acting together as a larger virtual telescope, can resolve some of the extended structure. Spectral modeling can infer where most of the light originates. Infrared observations can probe dust-enshrouded regions. All of these techniques must be combined to paint a consistent picture. And even then, the term size remains somewhat fuzzy, reflecting not a precise boundary, but a range of radii where the star transitions from opaque to transparent. In effect, when we say that a hypergiant's radius is a certain multiple of the Sun's, we are describing a large, glowing envelope whose outer limits are blurred, changing with time, and influenced by dust and wind. Their variability adds another layer of complexity. Hypergiants often show irregular changes in brightness. Their light curves, graphs of brightness over time, are not perfectly periodic like those of some pulsating stars. Instead, they can wander, brightening and dimming, sometimes with hints of multiple overlapping cycles, sometimes with sudden dips or surges in luminosity. These variations can be caused by pulsations in the envelope, episodes of enhanced mass loss, or changing patterns of convection on the surface. They may also reflect changes in the distribution of dust in the vicinity of the star, as new dust condenses or as existing dust is heated and dispersed. Occasionally, a hypergiant may undergo a more dramatic event, a large-scale ejection of material that significantly alters its appearance. Such events can produce new shells in the surrounding nebula. They can temporarily obscure parts of the star or change how its light escapes. The photosphere, the apparent surface from which most light emerges, may move outward into cooler, less dense gas after an outburst, or recede inward as material thins or collapses. In the star's spectrum, we see these behaviors encoded as shifting and splitting lines, absorption and emission features changing in depth and shape, signatures of gas at different velocities and temperatures. To truly understand these stars, astronomers must look at them across many wavelengths. In visible light, we see the star's photosphere and some of its nearby environment. But much of the structure around a hypergiant is dusty, and dust is more transparent in infrared wavelengths. Infrared observations show cooler material, the dust torus around WOHG 64, the extended shells around VY Canis Majoris, and the broader environment shaped by the star's winds. In radio wavelengths, we can detect specific molecules in the surrounding gas, and trace the motion of that gas through Doppler shifts. This reveals the speeds at which material is being expelled, the geometry of the outflows, and the presence of clumps and filaments. Spectroscopy, the study of the detailed distribution of light by wavelength, is especially powerful. By examining spectral lines from hydrogen, helium, and heavier elements, astronomers can deduce temperatures, densities, and velocities in different parts of the atmosphere and wind. Some lines appear broadened, indicating high-speed motions. Others are shifted slightly toward shorter or longer wavelengths, signaling gas moving toward or away from us. Wind-sensitive lines can show P Cygni profiles, features with both emission and absorption components, revealing outflows along the line of sight. Taken together, these multi-wavelength, multi-technique observations allow us to reconstruct a dynamic portrait of each hypergiant, not as a static sphere, but as a living, changing system of gas, dust, radiation, and sometimes companions. When you step back and simply let the images blend, you can imagine a gallery of hypergiants scattered throughout the galaxy and its neighbors. One, a red, bloated star with lopsided shells around it, light echoing off arcs formed by ancient eruptions. Another, enshrouded in a thick ring of dust, its visible light muted, but its infrared glow strong like an ember wrapped in smoke. Another still, a yellow, distorted star in close companionship with another, sharing an envelope, slowly exchanging mass, their combined light flickering as they orbit each other. And nearby, luminous blue supergiants, hotter, more compact, pouring out ultraviolet radiation, ionizing the gas around them, carving bright nebulae in the interstellar medium. All of these are variations on what matter can become when gravity collects it into particularly massive stars. As you lie quietly, you can let these different stars drift around you in your mind, not as sharp astrophysical diagrams, but as soft, glowing presences. A red hypergiant filling a vast volume of space, rings and arcs of gas around it. A yellow hypergiant in a close binary pair, slowly distorted by gravity's pull. A distant red hypergiant in another galaxy, wrapped in a dusty torus, its infrared glow reaching us across many tens of thousands of light years. A bright blue supergiant in Orion, its light already familiar to human eyes, even if its true nature is extreme. They all share a common thread. They live at or near the upper frontier of stellar size and luminosity. They are unstable, rapidly evolving, and short-lived. Yet from our vantage point, they are quiet, tiny knots of light against the dark. Knowing the depth of their reality, you can let that contrast soothe you. The universe contains these immense, storm-tossed furnaces, but it also lets you observe them from a safe, calm distance. Their violence becomes for you a slow, elegant dance described in numbers and models, transformed into gentle images and stories as you drift toward sleep. Hypergiant stars, with all their shells, winds, and uncertainties, become simply distant lanterns, each with its own history etched into the gas and dust around it. And somewhere above, on a clear night, some of their photons are arriving right now, touching the top of Earth's atmosphere, filtering down, and joining the rest of the starlight that has always watched over a resting planet. Deep inside a hypergiant star, far beneath the restless surface and the drifting winds, there is a world of crushing density and blistering heat, a place where matter behaves in ways that have no direct analog on Earth. If you could somehow descend, layer by layer, into the interior of such a star, you would pass through a series of regions, each with its own physics, its own role in the transport of energy from the core to the surface. At the very center lies the core, the engine that powers everything. In a hypergiant, the core temperature reaches hundreds of millions of degrees, and the pressure is so immense that individual atoms cannot remain intact. Electrons are stripped from nuclei, forming a dense plasma of charged particles, a sea of protons, helium nuclei, and heavier elements, mixed with a vast population of electrons and high-energy photons. Here, nuclear fusion proceeds at a furious pace. In stars like the Sun, the primary fusion process is the proton-proton chain, where hydrogen nuclei slowly combine to form helium. This chain is relatively gentle and operates efficiently at the Sun's core temperature of about 15 million degrees. In a hypergiant, those conditions are long surpassed. Core temperatures are high enough that another fusion pathway becomes dominant, the carbon-nitrogen-oxygen cycle. In this cycle, hydrogen nuclei still combine to form helium, but they use carbon, nitrogen, and oxygen as catalysts. The presence of these heavier elements allows fusion to proceed more rapidly at higher temperatures, making the cycle far more efficient at converting mass into energy. The result is a huge increase in energy generation. Every second, A hypergiant's core converts an enormous quantity of hydrogen into helium, releasing energy that radiates outward through the star, eventually emerging as its tremendous luminosity. As the star ages, this process changes. Hydrogen in the core is gradually depleted, replaced by helium ash. When the core is mostly helium, hydrogen fusion shifts into a surrounding shell, and the core contracts and heats until helium itself can fuse. Helium fusion produces carbon and oxygen, and later, as the core evolves further and contracts again, these heavier elements can take part in their own fusion reactions. Carbon can fuse to form neon, sodium, and magnesium. Neon can fuse to form oxygen and magnesium. Oxygen can fuse into silicon and sulfur. Silicon can fuse into a mixture of elements near iron. Each of these stages requires higher temperatures and densities than the one before, and each proceeds more quickly. Hydrogen burning in the core might last millions of years, helium burning hundreds of thousands, carbon burning only thousands, and silicon burning mere days. By the time the star approaches its end, its core has become a layered structure, different fusion reactions occurring in concentric shells, hydrogen burning in outer regions, helium burning inside that, followed by shells of carbon, neon, oxygen, and silicon burning, all surrounding an inner core increasingly rich in iron and related elements. If you could see this interior arrangement, it would resemble a glowing onion of nested spheres. Each shell is hotter and denser than the one above it, and each contributes to the star's total energy output. Above these fusion shells lies the envelope, the vast bulk of the star's radius. Through this envelope, energy created in the core must somehow travel outward until it can escape from the surface as light. In some regions, this energy is carried primarily by radiation. Photons scatter from particle to particle, gradually diffusing outward. In others, convection takes over. Large masses of hot gas rise, cool, and sink again, transporting heat by bulk motion. In a hypergiant, the envelope is so extended and the energy flux so intense that convection plays a major role. Instead of small granules like those seen on the sun's surface, a hypergiant can host convective cells that are truly vast. Each cell may span a significant fraction of the stellar radius, rising and falling over timescales of months or years. Within these cells, hot gas from deeper layers rises toward the surface, expands and cools, then sinks back down when it becomes denser than its surroundings. These flows are not uniform or perfectly symmetric. They create broad hot regions and cooler patches, producing a mottled, dynamic surface rather than a smooth, featureless disk. The scale of this convection is difficult to visualize. Imagine a single convective cell larger than the orbit of Earth, or even larger than the orbit of Mars, slowly turning, carrying energy outward in a grand slow-motion circulation. Overlaying this convective structure is the influence of radiation pressure. Every photon streaming outward from the core carries momentum. When these photons interact with atoms and ions in the envelope, they exert a tiny push. In most stars, this push is small compared to gravity, and the gas remains tightly bound. In hypergiants, the luminosity is so high that the collective push from radiation becomes comparable to the inward pull of gravity, especially in regions where the gas is partially ionized and more opaque. This leads to a constant interplay between radiation and gravity. In layers where the gas becomes more opaque, photons are trapped more effectively. Pressure builds, and the gas may expand. As it expands, it cools, its opacity changes, and the conditions shift again. This delicate feedback can drive pulsations, oscillations in which the outer layers alternately expand and contract, changing the radius and brightness of the star. It also contributes to the star's strong stellar winds. Where radiation pressure exceeds what gravity can hold, gas is effectively blown away from the star, accelerated outward to high velocities. This outflow is not a gentle breeze, but a supersonic wind that can reach speeds of hundreds of kilometers per second. At the surface, this wind can be fed by large-scale waves and shock fronts. Convection and pulsations drive disturbances upward. These disturbances steepen into shocks as they move into thinner gas, heating and accelerating material, helping to lift it out of the star's gravitational well. If you stood at the outer boundary of the photosphere and somehow could feel the forces acting there, you would sense a constant tug of war. Gravity pulls downward, radiation pushes upward, gas pressure supports from below, while the wind is continually being launched into space. The visible surface of the star is not a calm line, but a dynamic zone where gas is rising and falling, accelerating outward and sometimes being pulled back inward. The granules and convective cells on this surface are enormous. On the Sun, granules are about the size of small countries, and supergranules are about the size of continents. On a hypergiant, the equivalent structures can be larger than entire planetary orbits. One bright region could be wide enough to encompass the paths of Mercury, Venus, Earth, and Mars together. These giant cells move slowly in human terms, but steadily on stellar timescales. Their motion shapes the appearance of the surface and contributes to irregular variations in brightness. As some areas become hotter and more luminous, while others cool and dim. Deep below, photons begin their journey outward from the core. Even though the core is extremely bright, its photons do not travel straight to the surface. Instead, they undergo an enormous number of scatterings, being absorbed and re-emitted countless times by particles in the dense stellar interior. A single photon may wander for tens of thousands, or even hundreds of thousands of years inside the star, before finally escaping from the photosphere into space. This long diffusion time means that the light we see from a hypergiant today originated as energy produced in its core long ago. By the time it reaches the surface, it has lost all memory of its original direction, emerging as part of a smooth thermal glow. The result is the soft, radiant appearance of the star. A luminous sphere whose brilliance is the integrated effect of all that internal activity, smoothed and blurred by the diffusive transport of photons. Throughout the envelope, magnetic fields thread the plasma. These fields are generated and sustained by the motions of charged particles. As convection stirs the gas, and as the star rotates, the magnetic field lines are twisted and stretched, creating a turbulent magnetic environment. Magnetic fields can influence how gas flows. They can channel material into certain directions, guide the formation of structures in the wind, and contribute to localized heating and acceleration. In some hypergiants, magnetic effects may help explain spherical winds or the formation of particular arcs and clumps in the surrounding nebula, though the details remain an active area of research. At every scale, from the core to the outermost reaches of the wind, a hypergiant star is unstable by nature. Its extreme mass and luminosity place it in a regime where small changes can have large consequences. A slight increase in core temperature can dramatically boost fusion rates, leading to expansion and readjustment in the envelope. A modest variation in opacity in some layer can alter how readily radiation escapes, changing the local balance of forces, triggering pulsation, or enhancing mass loss. Convection can rearrange energy transport patterns, shifting where heat emerges at the surface, creating new bright regions and dimmer zones. Winds can remove mass from the outer layers, changing the gravitational field slightly, altering the pressure structure, and forcing the star to find a new equilibrium. All of these processes interlock, forming a complex feedback network that never fully settles. This is why hypergiants are often described as inherently unstable structures. They are not poised calmly at a single equilibrium point, but wander through a landscape of near equilibria, constantly adjusting, always close to tipping into a new configuration. And yet, from a great distance, this turbulent physics appears as a simple, steady light in the sky. The storms on the surface, the supersonic winds, the shock waves and convective cells, the photons spending tens of thousands of years diffusing outward, the layered shells of fusion around an iron-rich core, all of it is compressed in your perception into a faint star that rises and sets with the rotation of Earth. As you rest, you can hold both views at once. On one level, a hypergiant is a vast, unstable furnace, powered by fusion at hundreds of millions of degrees, structured by layered shells of burning elements, transporting energy through enormous convective cells, and living on the edge between gravity and radiation pressure. On another level, it is a distant, quiet point of light, part of a gentle pattern of stars, flickering softly in the night sky. Your mind can drift between these perspectives, from the microscopic interactions of particles in a dense plasma to the macroscopic image of a glowing orb suspended in the dark. You do not need to retain every detail, every reaction chain, every shell, every subtle mechanism of opacity and convection. It is enough to feel that inside each hypergiant there is a deep, layered structure, an organized complexity that arises naturally when gravity gathers so much mass into one place. And when fusion responds with such overwhelming energy output, the star's instability is not a flaw. It is simply the consequence of living at the extreme, where even light itself becomes a significant structural force, where radiation and gravity are nearly equal partners, and where matter cannot remain perfectly calm. Somewhere in the galaxy, hypergiant stars are living with this internal tension right now, their cores burning through the last stages of fusion, their envelopes churning and shedding mass, their magnetic fields twisting and reconnecting, their photon seas slowly making their way outward. And all of this happens while the star, from your vantage point on a small world orbiting an ordinary sun, remains a tiny spark in the darkness. You can let that thought ease you deeper into rest. Inside the universe's largest stars, complex physics unfolds in silence. The cores burn, the shells glow, the envelopes boil, and the winds blow. And beyond all of that, beyond the storms and the shells and the radiation pressure, there is the quiet, unhurried vastness of space, holding each star and holding you in the same deep cosmic night. Deep inside a hypergiant, beneath the convective envelope, beneath the layered shells of burning hydrogen, helium, carbon, neon, oxygen, and silicon, there comes a time when something quiet and decisive happens. The core fills with elements near iron on the periodic table. Up to this point, every major step of the star's life has been powered by fusion reactions that release energy. Hydrogen fuses into helium, helium into carbon and oxygen, carbon into still heavier nuclei. Each new stage of fusion provides pressure support, counteracting gravity, holding the star up against collapse. But iron and its neighboring elements occupy a special place. Fusing them into even heavier nuclei does not release energy, it consumes it. Instead of providing support, such reactions would sap the core of energy. As silicon burning proceeds, the core becomes increasingly dominated by iron group nuclei. The processes that built them up are rapid, and in the final days of the star's life, the core mass grows quickly. At first, degeneracy pressure from electrons helps support this iron-rich core, a quantum mechanical effect that resists further compression. But there is a limit to how much mass can be supported in this way. As the core approaches that limit, two things begin to happen almost simultaneously. Some of the highly energetic photons in the core become capable of breaking apart iron nuclei. This process, called photodisintegration, absorbs energy, removing pressure support. At the same time, electrons are captured by protons within nuclei, forming neutrons and releasing neutrinos. The loss of electrons reduces the electron degeneracy pressure, and neutrinos carry energy away. Together, these processes rob the core of both energy and pressure, and gravity suddenly gains the upper hand. When this tipping point is reached, the iron core can no longer support its own weight. It begins to collapse. The collapse is extraordinarily rapid. In less than the span of a heartbeat, the core shrinks from a region perhaps thousands of kilometers in radius to an object tens of kilometers across. As the core implodes, densities rise to values comparable to those found in atomic nuclei. Matter is compressed into a nearly uniform sea of neutrons. The collapsing material overshoots, reaches nuclear densities, and then stiffens dramatically as the neutrons resist further compression. This sudden stiffening causes the inner core to rebound slightly, sending a powerful shock wave outward into the infalling material. For a brief instant, there is a stalled shock front deep inside the star, pushing outward against layers that are still plunging inward. Neutrinos, created in vast numbers during core collapse, interact with this material, depositing energy and helping to revive the shock. If conditions are right, the revived shock wave races outward, tearing through the overlying layers and unbinding much of the star. From the outside, this event is seen as a supernova, a brilliant explosion in which the star suddenly brightens by many orders of magnitude, outshining its host galaxy for a short time. For a hypergiant, this final death is usually of the class known as Type II supernova. Type II simply means that hydrogen is still present in the outer layers when the explosion occurs. Hydrogen leaves a distinct signature in the spectrum of the supernova's light. Because hypergiants retain at least some hydrogen-rich envelope, Despite their strong winds, their explosions often fall into this category. The light curve of such a supernova, a graph of brightness versus time, may show a plateau as the expanding hydrogen-rich envelope cools and recombines. This is characteristic of many Type II events and reflects the physics of how energy diffuses through the expanding debris. In the central region, where the core collapse took place, a compact remnant is born. If the core mass after collapse remains below a certain threshold, the resulting object is a neutron star, a city-sized sphere of ultra-dense neutron matter, with a mass comparable to that of the Sun, or somewhat more. A neutron star has an intense magnetic field and can spin rapidly, emitting beams of radiation that sweep through space like lighthouse beams. When these beams cross Earth, we observe pulsars, regular flashes of radio waves or other radiation. If the core mass exceeds the neutron star's support limit, gravity continues to win. Even neutron degeneracy pressure cannot withstand it, and the core collapses further into a black hole. In that case, the star's central region becomes a space-time singularity, hidden behind an event horizon from which not even light can escape. The specific outcome depends on the initial mass of the hypergiant, the amount of mass shed by winds before collapse, and details of the core's evolution. For the most massive hypergiants, there is another possible fate, one that skips the iron core collapse step entirely. If the star's core reaches extremely high temperatures at sufficiently low density, conditions can allow a phenomenon known as pair instability. In such a core, high-energy photons can spontaneously transform into pairs of electrons and positrons. This conversion removes pressure-supporting photons, lowering the radiation pressure. When enough photons are converted into particle pairs, the drop in pressure allows gravity to compress the core rapidly. This compression raises temperatures even further, which accelerates nuclear reactions in a runaway fashion. In some cases, this runaway thermonuclear burning releases so much energy so quickly that it disrupts the entire star. The explosion is so complete that no neutron star or black hole is left behind. The star is unbound entirely, its material scattered into space. Such an event is called a pair instability supernova. It is thought to occur only in stars with very large core masses, roughly corresponding to initial stellar masses well above those of typical hypergiants. Though rare, they represent one of the most energetic ways for a star to die, whether through a Type II core collapse supernova, a pair instability explosion, or direct collapse into a black hole with only a faint or failed supernova. The end of a hypergiant is marked by the ejection of a vast quantity of material into space. The outer layers, enriched by the products of fusion over the star's lifetime, are torn away and hurled outward at thousands of kilometers per second, forming an expanding shell of gas and dust. This expanding debris is hot at first and glows brightly. As it travels outward, it sweeps up surrounding interstellar material, compressing and heating it. Over time, it cools and can form intricate nebula, rings, filaments, and knots. Many of the glowing supernova remnants we observe in our galaxy today, with their delicate filamentary structures, are the fossil echoes of such explosions. They are visual records of the star's final act, etched into the interstellar medium. In these expanding shells, we find heavy elements that were synthesized in the star's core, and during the explosion itself, carbon and oxygen made during helium burning, neon, magnesium and silicon from later burning stages, and elements heavier than iron formed by rapid neutron capture during the explosion. All are carried outward, mixed into the gas between stars. Over millions of years, this enriched material becomes part of the raw ingredients for new stars and planets. Clouds of gas and dust, seeded by the remains of previous generations of massive stars, collapse to form new stellar systems. Rocky planets are built in large part from elements heavier than helium, elements that originated in processes like those inside hypergiants and were dispersed by supernova. In this way, the death of a hypergiant is not only an end, but also a beginning. It is a mechanism by which the universe moves from simple compositions dominated by hydrogen and helium to more complex chemistries that enable planets, oceans, and life. The enrichment of the galaxy with heavy elements is a cumulative process. Each massive star that lives and dies contributes its share. Hypergiants, with their large masses, play an outsized role. Their cores achieve high temperatures and densities, producing large quantities of heavy elements, and their explosive deaths spread those products widely. After the brief glare of the supernova fades, the debris continues to expand. The velocities are high, but on the scales of interstellar space, the motion appears slow. Over 100 years, the shell grows larger. Over 1,000, it blends gradually into the surrounding medium. From a human point of view, the explosion is a dramatic, sudden event, but from the galaxy's perspective, it is a momentary rearrangement, followed by a long period of cooling and mixing. If you were able to watch this process in accelerated time, you would see the hypergiant's location flare brightly, then puff outward into a glowing bubble, which grows, dims, and eventually disperses into swirling filaments, finally merging with the diffuse material between the stars. Meanwhile, at the very center, the compact remnant persists. If a neutron star has formed, it may spin rapidly, with its strong magnetic field collimating beams of radiation from its magnetic poles. As the neutron star rotates, these beams sweep across space. If one of them happens to intersect Earth, we detect periodic pulses. Astronomers interpret such signals as pulsars, lighthouses formed from the cores of exploded stars. In some cases, if the initial hypergiant was rotating very rapidly before collapse, and if it retained enough angular momentum, the newly formed neutron star or black hole can power an even more extreme phenomenon. Jets of relativistic particles can be launched along the rotation axis, focused beams of energy that bore through the star's outer layers and propagate into space. When such a jet is oriented close to our line of sight, we may observe a long gamma-ray burst, a brief but intense flash of high-energy radiation, lasting from several seconds to minutes, followed by an afterglow at lower energies. Long gamma-ray bursts are thought to be associated with the collapse of particularly massive, rapidly rotating stars, some of which may have been hypergiants or related types. These events are rare, but they represent some of the most energetic explosions we can observe, releasing more energy in a short interval than the Sun will emit in its entire lifetime. Not all hypergiant deaths are so luminous. In some scenarios, the core collapses directly into a black hole, with much of the rest of the star falling in as well. The shock may be weak, or may fail to eject most of the envelope. In such failed supernova, the star appears simply to vanish from the sky, dimming gradually as its outer layers are swallowed, leaving behind a newly formed black hole with little or no bright explosion. Astronomers have begun to search for such disappearing stars, monitoring luminous red supergiants and hypergiant candidates over many years, looking for cases where a star is present in earlier images but gone in later ones, with no bright supernova observed in between. These quieter endings are a reminder that not every massive star dies in a blaze of light visible across the universe. Some slip into darkness almost silently, their collapse revealed only by the absence of their former glow. When we compare hypergiant supernovae with those of more ordinary massive stars, we find a spectrum of behavior. Less massive stars, perhaps 10 to 20 times the mass of the Sun, can end in core collapse supernovae that leave behind neutron stars. Their light curves and spectra may differ from those of hypergiant explosions because their envelopes are less extended. Their mass loss history is different, and their internal structures somewhat less extreme. Hypergiants, with their larger masses, stronger winds, and more heavily processed cores, can create more massive remnants and more complex surrounding nebula. Their explosions may be more luminous, or may interact strongly with dense shells of gas previously lost in eruptions, producing distinctive signatures in their spectra. In some cases, a hypergiant's explosion may be shaped or brightened by this circumstellar material. The supernova shock collides with dense gas close to the star, converting kinetic energy into radiation. This can produce especially bright or long-lasting supernova, as the shock plows through the surrounding medium. Yet despite these differences, the underlying narrative is shared. A massive star is born, burns through its fuel rapidly, forms an iron core, and eventually can no longer resist gravity. The core collapses, a shock is launched, and the outer layers are expelled, leaving behind a compact remnant and an expanding shell of enriched material. In hypergiants, this story is amplified. The masses are larger, the luminosities higher, the winds stronger, and the final explosions, or collapses, especially significant in shaping and enriching their surroundings. As you rest with these thoughts, you can imagine a hypergiant at the moment just before its end. From the outside, it is still a swollen, luminous star, its surface unhurried, its winds flowing, its light crossing space as it has for millions of years. Inside, the last stages of fusion are racing to completion. The silicon-burning shell is rapidly building an iron-rich core. The core is approaching the threshold beyond which it cannot support itself. Then, in less than a second, everything changes. The core collapses, a shock is born, and the star's outer layers are set on their outward journey. From a safe distance, perhaps millions of light years away, you might see only the brightening and fading of a point of light over months, followed by a slowly expanding remnant visible to telescopes for thousands of years. From the galaxy's perspective, a heavy element factory has completed its work, dispersing its products into the interstellar medium, making future worlds and life chemically possible. And in your own mind, this entire process becomes a calm, slow-moving sequence of images, a long, gentle exhalation of a giant star that began as a cold clump in a distant molecular cloud and ended as an enrichment of the cosmic sea. The death of a hypergiant is dramatic in physical terms, but you can let it arrive here as something tranquil, a natural transition in the life cycle of matter, another way the universe rearranges itself, quietly, patiently, over spans of time far beyond a human life. You are free simply to float alongside this story, watching a titanic star live, burn, collapse, and return its substance to space, while you, on a small, cool world, rest under a sky that still holds countless other stars in various stages of their own. Endless, cosmic journeys. Imagine the Milky Way not as a collection of individual stars, but as a vast, breathing ecosystem. Gas and dust flow through its spiral arms, cooling, collapsing, forming new stars, and being heated and stirred again by those same stars as they live and die. In this galactic ecology, hypergiants are rare, but they are powerful agents of change. Every hypergiant begins as an over-concentrated pocket of matter, a place where gravity has gathered far more mass than usual into a single star. Because of that, its life is brief, its light intense, and its influence disproportionately large. One of the most important roles hypergiants play is that of chemical enrichment. They begin their lives in a universe that is mostly hydrogen and helium, with only a small fraction of heavier elements inherited from earlier stellar generations. Deep in their cores, as they progress through their fusion stages, they manufacture a rich inventory of heavier nuclei, carbon and oxygen during helium burning, neon, magnesium, and silicon during later burning stages, and elements near iron as the final core products. Some of these elements leak out slowly through stellar winds. Hypergiants lose mass at extreme rates, so their outflows can carry not just hydrogen and helium, but also processed material dredged up from deeper layers, enriching the surrounding gas even before the star dies. When the star finally ends its life in a supernova, it releases the rest of its fusion products into space, along with the elements made during its normal burning stages. Additional heavy elements are created during the explosion, where rapid neutron capture can assemble nuclei heavier than iron. The expanding debris carries this entire mix outward, blending it into the interstellar medium over time. Every future molecular cloud that passes through such enriched regions, every new generation of stars forming in that gas, inherits the chemical fingerprints of those hypergiant lives. The carbon in organic molecules, the oxygen in water, the iron in planetary cores, all trace part of their history to massive stars, and hypergiants, with their large initial masses and efficient heavy element production, are among the most generous contributors. But their influence is not only chemical, it is also dynamical. Hypergiants inject energy and momentum into their surroundings throughout their lives. Their intense radiation ionizes nearby gas, stripping electrons from atoms, creating ionized regions that glow in ultraviolet and visible light. These ionized zones are often seen as bright nebulae around young, massive stars in star-forming regions. Within these bubbles, gas is heated and driven outward, creating pressure fronts that push against the surrounding molecular cloud. Sometimes this compression can trigger new star formation by squeezing nearby gas to the point where gravity can take over. At other times, the energy input can disperse clouds, halting further star formation in that local region. On larger scales, the combined winds and radiation from clusters of massive stars, including hypergiants, can carve out cavities in the interstellar medium, vast bubbles filled with hot, tenuous gas bounded by shells of denser material. These structures can span tens or even hundreds of light years, and over millions of years, they can merge, intersect, and reshape entire portions of a galaxy's gas distribution. When a hypergiant finally explodes as a supernova, it adds an additional surge of energy. The shock wave travels outward, further heating and stirring the gas. The shock can compress nearby cold clouds, triggering star formation along its path, or it can contribute to clearing and diluting the gas, depending on the configuration. In this way, hypergiants participate in a feedback loop. They are born from dense molecular gas, grow rapidly, and then through winds, radiation, and explosions, they modify the very environment that birthed them, sometimes promoting the next cycle of star formation, sometimes delaying it. Their influence is not uniform or simple, but it is significant. Zoom out further, beyond the Milky Way, and consider the early universe. Shortly after the Big Bang, the cosmos contained almost no elements heavier than lithium, just hydrogen, helium, and trace amounts of a few light nuclei. When the first stars formed, they did so in a pristine medium, with no pre-existing dust, no previous generations to enrich the gas. Theoretical models suggest that under those conditions, star formation may have favored very massive stars. The cooling processes in such metal-poor gas differ from those in later, enriched environments, making it easier for large clumps to remain intact and form single, massive objects. These hypothetical first-generation stars are often called population 3 stars. They may have included supergiants and hypergiant-like objects, with masses far exceeding even the largest stars that form commonly today. If such early titans existed, they would have lived extremely short lives, burning through their fuel rapidly and dying in powerful explosions, including pair-instability supernovae for the most massive among them. Their deaths would have provided the first significant injection of heavy elements into the universe, seeding the primordial gas with carbon, oxygen, and other nuclei needed for more complex chemistry. Their intense ultraviolet radiation would also have contributed to the process of reionization, the epoch when the initially neutral hydrogen in the universe was gradually ionized by the first luminous sources. In that sense, hypergiant-like stars in the early universe helped transform the cosmos from a dark, simple medium into one where galaxies, nebulae, and chemically richer structures could emerge. Although we do not yet observe these first stars directly, we infer their existence from the chemical patterns in ancient metal-poor stars and from cosmological models. When we study hypergiants in the local universe today, we are not only learning about present-day astrophysics, we are also gathering clues about those early distant epochs when the upper limits of stellar mass were being explored in a more pristine cosmic environment. Back in the modern Milky Way, hypergiants mark the upper edge of what a star can be. There are physical limits to how massive and luminous a star can become, and still hold itself together. At very high masses, radiation pressure in the interior becomes so strong and mass loss so intense that adding more mass does not produce a correspondingly larger, long-lived star. Instead, the star sheds material rapidly, or becomes unstable, or fails to form in the first place because its radiation halts further accretion. The precise upper mass limit is still a topic of research, and likely depends on metallicity, rotation, and environment. But hypergiants sit close to this frontier. They are natural laboratories for testing our understanding of this upper edge. If our models predict that stars above a certain mass should be unstable, or should lose mass at given rates, we can compare those predictions to what we observe in hypergiants. Their winds, spectra, and variability patterns all provide constraints. Because hypergiants are so rare and short-lived, they also highlight the statistical nature of stellar populations. In a typical star-forming region, the distribution of stellar masses follows a pattern, often called the initial mass function. Many low-mass stars form fewer intermediate-mass stars, and only a tiny fraction become very massive. Hypergiants occupy the extreme tail of this distribution. For every hypergiant you might find, there are vast numbers of smaller stars, quietly burning for billions of years. On galactic timescales, hypergiants appear briefly, flare in influence, and vanish, while the more numerous small stars carry the light of the galaxy steadily onward. This contrast underscores an important truth. The most massive stars are spectacular, but they are not the typical actors in the cosmic story. They are rare, temporary participants, whose main legacy is to reset conditions around them, injecting energy and heavy elements into the galaxy before leaving the stage. Despite their scarcity, hypergiants are invaluable to astrophysics as laboratories of extreme conditions. Their cores reach temperatures and densities that push fusion physics to its limits. Their envelopes operate in regimes where radiation pressure, convection, and turbulent opacity interact in complex ways. Their winds test our understanding of how radiation can drive mass loss and how magnetic fields and rotation shape outflows. By observing hypergiants in detail, astronomers gain data to refine models of stellar structure and evolution. High-resolution spectra reveal wind speeds, density profiles, and chemical abundances in their atmospheres. Interferometric imaging can resolve their extended surfaces and circumstellar material. Infrared and radio observations map their dust and gas environments. Each piece of information helps improve our theoretical descriptions, which can then be applied to other massive stars, to supernova progenitors, and to the interpretation of distant galaxies. Where individual stars cannot be resolved at all, hypergiants thus act as calibration points for our understanding of extreme stellar physics. They also intersect with many other domains. Core collapse supernova theory depends on accurate progenitor models. Neutrino astronomy connects to the physics of collapsing cores. Gravitational wave observations of merging neutron stars and black holes are linked to the end products of massive star evolution. In each of these areas, knowing how hypergiants live and die helps set initial conditions, masses, spins, and compositions of the compact remnants they leave behind. Even the large-scale evolution of galaxies is affected. Simulations of galaxy formation must include recipes for feedback. The way stars, especially massive ones, heat and stir the gas. These recipes depend in part on how we think hypergiants and other massive stars behave, how much energy their winds and supernovae return to the medium, and how they regulate future star formation. So while a hypergiant might be just one star, in one location, its physics echo outward into models and theories that describe entire galaxies and the universe at large. And yet, for all their power, hypergiants are fleeting. A hypergiant's total lifetime may be measured in a few million years. Its hypergiant phase may last only a fraction of that time, just a brief, unstable period between more ordinary evolutionary stages and final collapse. Compare that to the age of the Milky Way, on the order of billions of years, or to the age of the universe, also billions upon billions of years. On those scales, a hypergiant's existence is like a short, bright flare, quickly rising, powerfully affecting its surroundings and fading, while the galaxy continues its slow rotation, and the cosmic web continues its vast, silent expansion. Even the largest stars, the most luminous and massive objects of their kind, are temporary patterns in the flow of matter and energy. Their brilliance is borrowed from the potential energy of gravity and from the mass converted into light in their cores. When that reserve is spent, the pattern dissolves and the matter is redistributed. The atoms that once formed the hypergiant's heart and envelope, its shells and winds, are not destroyed. They are mixed into the interstellar medium, incorporated into new stars, planets, and perhaps even living beings, somewhere, sometime. Hypergiants remind us that nothing in the universe, no matter how immense, is permanent. Everything transforms on timescales appropriate to its scale. Planets, stars, galaxies, clusters, all have their own cycles, their own beginnings, middles, and ends. As you let this perspective sink in, you may feel a kind of quiet reassurance. The same physical laws that govern the life and death of hypergiant stars also govern the smaller processes closer to home. They apply equally in your own body, where nuclear fusion does not occur, but where gravity, electromagnetism, and quantum mechanics still shape every atom and every molecule. You are made, in part, of matter forged in stars, possibly in hypergiant ancestors long gone. Your calcium, your iron, your oxygen, all carry the imprint of fusion processes that once lit some distant part of the galaxy. Hypergiants, therefore, are not only remote curiosities. They are part of your own history, written on a scale far larger and slower than a human lifetime, but connected to you through the simple fact that you are built from their ashes. Somewhere out there now, a hypergiant is nearing its end. Its core layers are burning through the last stages. Its winds are sculpting the surrounding gas. Its light is streaming outward, crossing interstellar distances, perhaps already on its way toward Earth. To arrive long after you fall asleep tonight, you do not need to know which star it is or when its light will reach this planet. It is enough to know that such processes are ongoing, quietly, persistently, in the background of the universe. As you lie still, breathing slowly, you are sharing this moment with hypergiants, with newborn stars in molecular clouds, with ancient white dwarfs cooling in the dark, with galaxies colliding in remote clusters, all part of the same continuous, unfolding story. Hypergiant stars mark the extremes, the upper limit of what a single star can be. They live fast, shine fiercely, reshape their surroundings, and then pass away, leaving behind enriched gas, compact remnants, and a slightly altered galaxy. In the long arc of cosmic history, they are brief, but they are also essential. Knowing this, you can let your thoughts drift outward, beyond your room, beyond your planet, into the spiral arms of the Milky Way, where these titans are born, live, and die. And then gently, you can let those thoughts fade, like the afterglow of a distant supernova, until all that remains is a calm awareness of a universe that is vast, dynamic, and deeply, quietly interconnected. Out beyond the reach of city lights, beyond clouds, beyond even the faintest glow of the atmosphere, the sky is filled with stars you will never see with your eyes alone. Among them are the quiet remnants of hypergiants that have already lived and died, and the soft light from those that are still burning now, far away, in the spiral arms of galaxies scattered across the universe. Tonight, you are not required to keep track of their lifetimes, or their fusion chains, or the details of their winds and shells. You can simply hold one idea gently in your mind. There are stars out there so large that if they were placed where the sun is now, they would swallow the orbits of the inner planets. Their surfaces would extend far beyond the path of Earth, their atmospheres stretching into regions that are empty space for us. These are the hypergiants, the titans of the cosmos, engines of light and heavy elements, brief, unstable giants living at the limit of what a star can be. They shine with a brilliance millions of times greater than the sun, yet from here their light arrives as a thin, delicate thread, a few photons at a time, whispering across space. There is a kind of calm in that contrast. Inside, they are places of intense heat and pressure, cores at hundreds of millions of degrees, shells of fusion nested like glowing spheres, convection cells larger than planetary orbits, and winds faster than anything we know on Earth. Outside, seen across thousands or tens of thousands of light years, they are just points, soft glimmers folded into the deep black of the night. The universe does not need you to solve this, or to fully understand it. It simply invites you to notice that even its wildest extremes, its most luminous and short-lived stars, are part of a larger, slow, unhurried pattern. Hypergiants ignite, expand, shed their layers, and finally collapse or explode, returning their substance to the galaxy, enriching the gas from which new stars and planets will someday form. Their light fades, but the elements they forged remain, hidden in clouds in future solar systems, and in the bodies of beings who, much later, look back up at the sky and wonder where it all came from. The same atoms that once moved through the hearts of such stars are now part of you. Traces of carbon, oxygen, iron, and other heavy elements were built in long-vanished massive stars, some of them perhaps hypergiants or their cousins. Their death seeded the galaxy, and that enriched matter eventually found its way into the clouds that form the sun, the earth, and all living things upon it. So when you think about hypergiant stars, you are not thinking about something completely separate from yourself. You are thinking about an earlier chapter of the story that eventually led to you lying here, breathing slowly, under a sky threaded with starlight. Far above, those titanic stars continue their quiet work. Some are just beginning to swell and grow unstable. Some are in the midst of casting off shells of gas and dust. Some have already ended, leaving behind neutron stars or black holes, and expanding nebulae that will one day dissolve into the interstellar medium. On the timescale of galaxies, all of this happens gently, gradually, like slow tides in an ocean of gas and stars. On the timescale of a single night, nothing in that distant choreography needs your attention. It unfolds whether you think about it or not, steadily, reliably, with a patience that spans millions of years. You are free now to let the images soften. Enormous red spheres fading into darkness, blue-white giants shimmering at the edge of stability, great shells of gas drifting outward as delicate nebula, all of it receding into a comfortable background glow. You can feel your own breathing as a quieter rhythm, much smaller in scale, but guided by the same physics that shapes stars and galaxies. Gravity holds you to your planet, just as it holds stars in their orbits around the galactic center. Atoms in your body obey the same quantum rules as the atoms in a hypergiant's core. You are made of the same kind of matter, living in the same universe, under the same physical laws. As you drift towards sleep, imagine yourself floating far from Earth, in a place where you can see the Milky Way as a full, luminous arch, spiral arms glowing softly, dark lanes of dust veiling some of the light. Hidden within that glow are the hypergiants, rare, brilliant, and fragile. You do not need to find them, or name them, or remember their statistics. It is enough to know they are there, breathing in their own immense, slow cycles, while you settle into your own quieter one. The night around you is deep and patient. The universe is vast and busy, but also, in its own way, very still. Let that stillness reach you through the knowledge that even the greatest stars flare briefly and fade, while the cosmos carries on calmly, endlessly. You can rest inside that understanding, small, safe, and gently held, under a sky that has room for everything, from tiny grains of dust to the titans of the cosmos, and for you here breathing, drifting, and finally sleeping.